Hi everyone, my name is Rocco Michele Lancellotti and I'm here with my colleague Gennaro. We are data scientists working data reply and we'll talk about some application in industry here in Italy. Briefly, we will explain who we are, just 2 minutes. Then we will go deeper in the deep learning topics with some application, as you can see just from the agenda. Reply is a group of companies. We make consultancy with our clients in Italy. And we work on every different aspect of technology. Today, we are from data reply, and we deal with big data and machine learning, as you can see from the slide here. So we cover end-to-end big data projects with machine learning or data science and machine learning content in it. And we deliver this to the client, to our customers. So what we cover, as you can see, is everything from data science to advanced aspects of machine learning, since artificial intelligence is still a hard task to deliver in reality. So differences, data science, as many of you I think knows, refers to techniques where human is supported by a machine and we try to extract information and insights from data. We have here the classical prediction models. Then we deal with the machine learning, which is the science to create algorithms and programs which learn from data, heterogeneous kind of data. When we reach the maximum amount of automation, which is no human at all, we have intelligent agents, and then we have artificial intelligence. Just going briefly in deep learning can be defined as the implementation of machine learning. So that is to say, an implementation technique based on neural networks. As you know, deep learning during the last years came up so strongly because we have big data today and hardware to support big data processing. I think that all of you know what is an artificial neural network. How many of you don't know what is an artificial neural network? Everybody. So, just to be brief, we always have an input layer, an output layer, and some layer in between. What happens? You give some data at the input layer level, and we have some results. What kind of results? Some tasks are control, classification, prediction, approximation. Some problems supervised or unsupervised. In the middle, you have hidden layer, which makes the feature learning process, giving the output according to some nonlinear transformations. If you have many hidden layers, you talk about deep learning. That's all. On the right, you have some general use cases and the industry related where these use cases have been used. You know, this is a famous chart. You can have from the simplest one to the more complex one. There are so many types of different artificial neural networks. Today, we focus on the image applications. So in this field, we can say that the convolutional neural networks are the most used ones. The difference is that you give to the input layer an image. Imagine each neuron is a pixel with a content of information. Then you have layers about convolution, which try to extract features from the single subframes of the image. Pooling layers, which are able to summarize the most relevant information within each subframes. And at the end, a fully connected neural network which is able to classify in this case, in the classification case. Sorry for the Italian, this means starting from an image of a car, damaged car, I want to know if this car is damaged or not. Sorry for the Italian here. And now we come to the more interesting part. Industry application. Those are the main areas: self-driving vehicles, medical imaging, satellite imagery analysis, object segmentation, face recognition, and handwritten text recognition. The one in greens are the one that we are working on. We already have some results, and now we are here to share with you two of them. The first one is the satellite imagery analysis, and I give the word to my colleague Gennaro.
I'm supposed to use this, right? Okay. Hi, everyone. So I'm going to tell you a bit about what we did on satellite imagery analysis. So why is it interesting? So for instance, a lot of government agencies have a stake in this. You could, for instance, using satellite imagery, measure the wealth of a neighborhood, or detect environmental crimes, or analyze crop types. You might want to do that too. Or even analyze land use. For instance, if you want to measure the wealth of a neighborhood in a very rough way, you could count the number of swimming pools. So you have a satellite image, and so it's taken from satellite. You can tell how many swimming pools there are, and if none of the people there has a tax return or there's filing, everybody is filing like 0, there's a problem. This is just to be like, this is a very rough example. Okay, so I'm gonna focus mostly on land use, but you could do anything with the results essentially. So this is more of a general purpose introduction. So first, you need to know, let's say you want to detect whether there are trees or houses or crops or roads in a given picture. So first, you have to classify, and you want to do it in an automated way. You have to classify the image and say whether it contains or not one of the classes you're interested in. And for the purpose of classification, what we used is transfer learning. So there are various solutions available for free on the internet already, and as you can see here, the most accurate are the INCEPTION class. But okay, also the ResNet and VGG do very well. Anyways, we focus on the INCEPTION v3 because it's better supported and has a great TensorFlow API for retrain. So the task, as I was saying, is image classification, and what you do is you take all this, and it's given, Google given, instead of God given, right? Okay, and all of this, like all of the network was trained already, and you can find weights already computed for you. And this was trained on, this is something that resembles to INCEPTION v3. Actually, the actual picture will be in the next slide. But it was trained on 14 million images, and it was classifying a single label, I think, about objects in 1,000 classes. Okay, as you can see, the blue is convolution, the red is pooling, which might be average or max pooling, the yellow is softmax, and green is normalization or concatenation. So which of these are you retraining? Well, none of these, because there was a part missing, and that's exactly what you're retraining. So it's very it's a computationally easy thing to do after you tweak the code a bit. So what INCEPTION does for you, which is the most computationally intensive part, is extracting features from your extracting features. So you have the predictors already built for you. So it's a bit like heavy-duty feature engineering done already for you. And what you retrain is just the classification part, which is the fully connected layer over there. Okay, so okay, we repurposed the usual TensorFlow script to do multi-class, multi-label, because we were interested in a problem that required that. And so we also found a lot of work already done for us on GitHub. And one example of this is the TensorFlow for Poets repo. So this is an example of the retrain call. You have, okay, you have to specify where your images are, where the labels are, and all, so on and so forth. The most interesting thing is that you can also specify how many epochs you want to retrain. So your fully connected layer at the end will be trained the number of, this is not exactly the epochs, but you can deduce the epochs in those, from those steps. Okay, so after repurposing the TensorFlow script, we went on and got about 90% accuracy on the 5 classes we were interested in. So buildings, road, trees, track, crops. So what happens when you know that an image contains a class, an object belonging to a class, but you also want to know where the object is. So you start doing segmentation. So this is this is way more than what we did, but it's a great example, and it's great work from Facebook research, and it's mask or CNN. R is for regional, and CNN is convolutional neural network. Regional because, as you can see, everything is boxed, so it proposes also boxes to encase the various objects you're looking for. But okay, as I was saying, this is for the time being for us. This is what we would like to do in the future, maybe near future. My colleague Tommaso is an expert on that, and so okay, we wanted to start from something simple and something that we could make work as quickly as possible. So we started from what is actually something very good. Does not as many things as mask or CNN, but it does semantic segmentation. So exactly what I was saying. It tells you when you have a class in an image, it tells you every single pixel that has that class. So I don't know, swimming pools, and it tells you, and you can highlight. You have a mask that covers every swimming pool, like a mask of pixels. So, okay, and I just said that you just work directly on the pixels. The training is somehow pixel-wise. It's a very smart way of doing this. It's by the very fact that you start from this kind of very clever way, very wise way of using images, you can have very good results even from very few images. Like the Kaggle challenge, we took images from, for the purpose of this presentation, as I think 30 images or 25. Anyways, so it's not that many. Consider that INCEPTION was trained for another purpose, but usually you train on millions of images. So, and these are the authors of the original UNET paper: Ronenberger, Fisher, and Brox. Okay, let me tell you a bit about UNET. Okay, it's U-shaped, as you can see. It's basically, well, basically built on the structure of a convolutional neural network. And it's pretty fast. And it includes something that is not always something you do before sometimes when you use a convolutional neural network, augmentation, but this is specifically designed to do upsampling. So it has something that resembles to an encoding part, so you compress your images. This is not the network we used, actually, but it's exactly the same idea. Okay, so the red arrows are usual max pooling, which somehow resemble, so the all cascade here resembles somehow an encoding part. And then you have the upsampling parts, which in our case are just, okay, I'll tell you more about this, but you double the size of your images and essentially that's it. So you augment your data set in that way. And what else? So you also want to prevent your network from losing too much information along the way. So what you do is you just crop and paste on the last layers. And okay, here's the code. So we repurposed this Kaggle kernel essentially from it was from one of the Kaggle kernels, and actually Keras has already an upsampling function. So this is to tell you a bit about the gray arrows of UNet. So for instance, up6 is just a merge of the upsampling on the previous layer. Okay, this is not a great example, but probably, okay, this, up7. It's a merge of upsampling of convolution 6, which is the previous layer, but with convolution 3, which is up here. Okay? And this prevents you from losing too much information. Keras does this upsampling by doubling the size and interpolating for the pixels that are in the middle, the ones that are left blank. Okay, so for classification, usually, well, you could use accuracy. That's a standard metric for measuring the performance of your network. For semantic segmentation, a very good metric is the Jacquard coefficient, or the intersection of reunion. And essentially, let's say this is your mask. This is the actual pixels where your class is present. You intersect the two, you compute the area, and you divide that by the union of the two sets. And okay, if you have very bad classification, you get 0. That your mask is not getting any of the pixels. Or if you have very good classification, you get a 1. That's the best score you can get. And here are some of the results. So these are the buildings. So you see they're yellowish because this is the mask the color we picked for the mask. Here are the tracks. Here are the crops. Here are the trees. And this is something interesting, even though we cut it out from our what we eventually used, but these are all classes from the Kaggle challenge we took our data set from. So this is a waterway, and this water is still moving, is connected to the river, and this is standing water. So it can even tell you the difference between those two. That's, I don't know, I thought it was pretty cool. Okay, so what about computing land use? So land use rate, it's pretty easy, but the heavy lifting was done before this, of course. You don't need a math PhD to take this ratio. You just take all the pixels that are white here, you sum them, and then the area of this image, suppose this is geolocalized, And so you know exactly where the white pixels are in real life. But you want to know, let's say in this area, you want to know what's the ratio of land use. And you just take the ratio of this pixels with the area of the image. Okay, for the future, okay, first it was pretty, let's say, it wasn't easy, but computationally it was not too hard. We didn't use any GPUs for our retrains. For instance, for the INCEPTION, you can do it on your own computer, even if you don't have a GPU. Instead for UNet, we found ways online, starting from the Kaggle challenge. And okay, we would like to do more and use MASCAR CNN on the same data. And some other thing that this is inspired by what MASCAR CNN and its predecessors do, Fast and Faster Art CNN, is analyzing real-time video feeds. And this is something we would like to do in the future. And now I'm gonna hand over to my colleague. Okay, these are the references and actually credits and resources we used. So this is the original paper. This is the great Kaggle kernel we repurposed. This is the great GitHub script that was repurposed from INCEPTION, the original INCEPTION to do, and which we repurposed to do multi-class, multi-label. And this is the original TensorFlow for Poets repo from Google. Okay, and now.
Thank you, Gennaro. Let's continue with another application, which is car damage recognition. This is the context. You know, crash events are events that nobody of us want to be involved in. If it happens, they can be really unsatisfactory events, both on the personal side and on the, you know, the process of reimbursement from the insurance company. So the idea is to create an app which is able to estimate the repair reimbursement amount just from the pictures taken from the insured driver. This is the idea. Those are the technologies we used on data preparation, model development, web app development, everything with Python. We started from the pictures taken from crashes from our client. In this case, there were millions of images, but not just car images. Also documents, people in the middle of the car, or just car components on the floor, imaging everything. We used Amazon and Mechanical Turk to give a label. After, you know, a filtering of those images, we created a manual, the labeling manual. We gave this manual to our friends of Amazon Mechanical Turk, and then they give us labeled, coherently labeled images. We developed with Keras and TensorFlow a set of models that we used together, or, you know, I cannot say a lot on this because we have a non-disclosure agreement on this project, but we used many different kinds of convolutional neural network, and not only that, with some models that gave us a good accuracies, we will see later. On the web app side, we used the Flask, and everything was on Google Cloud Platform. This is the workflow. From the pictures, first check, we check with convolutional neural networks, if there is a car or not in the image, easy. We check if this picture has been already used in past claims, and so that could be a fraud. We also check the license plate. If it's not possible, because maybe it's missing or it's destroyed, or we just connect to the information of the driver and we put it manually in the app and we proceed. The first step is the recognition of the car model. The second step is the car view. If we are looking at the picture which is the front of the car, the side of the car, or the back of the car. Why this? To be more precise in the third most important step. Which components are damaged and which are not. This is just a subset, the main ones that we started from. Using, in this case, image segmentation, it was really useful in detecting bonnet, left, right, front lights, bumper, wheel arch, and so on. At the end, we have the last step, which is like determine the threshold of the repairment costs. If we are below, we pay it directly. If we are above, just you have to go through a deeper process for the reimbursement. Yeah, in this case, it's not only based on images, but also on the historical data of past accidents. So we had all the data of repairments in the past car accidents. Those are some results. As I told you, this is the most difficult task because we have first to distinguish the part and see if it's damaged or not, comparing it with the original part. And consider this for every different car model. The lower bound is 75% when you do not have like around 100 of different images of one single part. When you have more than 200, 300, you go above, and you have an accuracy that is usable in production, if you want to use an app that does this job. Clearly, best performances comes from the most represented car models in your data. If you just have one accident with a particular car, it's very difficult to understand how much money you have to reimburse to this driver for the accident. Some limitation. It's not so easy because 78% of the time has been used for the training set preparation. As I told you, we started from millions of images and we came up after a long and tiring process to the labeled images where we started to build some algorithms finally. The training time, if it's not a big deal when you are in the case of hundreds of images for every single part. Otherwise, you have to start using generative adversarial networks, and it starts to be a bit difficult from this side. The real-time usage, all this process has to last like some seconds, 10 to 15 seconds, because the idea is that you have to use your app and you have the message back in some 15-20 seconds maximum. And the production accuracy level, since we want to deliver a product, a data product that has to be used by our client, we have to reach those accuracies. How we reach those accuracies? Applying business rules, applying strict thresholds when we classify, especially the damaged parts. So, as you can imagine, is an iterative, it's a cycle. We just classify damaged parts, and then we have to pass through a set of business rules that the company gives to us to understand really when they can pay directly or not. With this, I finished. I thank you for your attention, and I forgot to name our third colleague, Tommaso, which is over there, which made a strong contribution to our projects. And if you have any question, thank you. And yeah. Yeah.
So I work in an insurance company and I work on a similar project. So can you speak in private for develop with our company for automatic payment of the image? It's an interesting idea.
Yeah. We can talk about this. Thank you.
Hi, I have two questions. I was looking at the results slide.
Yeah.
So from that slide, it seems that you have a different one model to distinguish the car model and one model to distinguish the view. So the step when you consider the damaged parts, okay, the damaged components, do you have here n different models for each combination of car model and car view?
Yeah.
Okay.
A big burden, but it's in this case for this application it's needed.
Okay. The second question is before you cited GAN regarding, I think, the question is if you used GAN for data augmentation in the sense that I think that for some combinations of car model and car view, there is a lack of images in the data set. So I was wondering if you use GAN for data augmentation and generating more images for the data set.
Generating more images to help these cases to classify better when it's damaged and when it's not. Yeah.
Okay, thanks.
Other question?
It's like the Pokemon case, you know. There are the original Pokemons, the strange Pokemons. That is the idea.
Okay. Thank you, Rocco, and thank you, Gennaro.
Thank you.